Swayam Prabha. Digital India. Educated India.
So we have discussed this formulation behind birefringence. We spoke about the origin of the two refractive indices. We talked about the optical axis, and then I also discussed the effect that this existence of the two refractive indices has on an incoming wave. So if the optical axis is perpendicular to the propagation direction, the polarization vector in general, the two components of the polarization will propagate at different speeds, and so they will interfere as the light ray exits the material, and as a result you will see a phase difference, and that phase difference is what we are going to pick up in the form of fringes, right. And we briefly alluded to these fringes. I spoke about the origin of this difference in the refractive index for photoelastic materials, and the fact that this n1 minus n2 was proportional to sigma 1 minus sigma 2, the principal stresses, and we ended with this basically, right. So here we were talking about the 5 steps that we are going to follow, which is take a given light with a given wavelength spread spectrum typically, and then we pass it through a linear polarization sheet with a polarization in the y direction, which we call P, and then the polarized light passes through the sample, and from the sample it goes to a second crossed polarizer called the analyzer or A, which has its polarization direction in the x direction, and then we look at the output of the light that is coming out of the analyzer, right. So it is simple enough to set this up at least schematically. So if you draw again the same 3-dimensional figure that we put up last time, you have your light source. I will assume that the propagation direction is z, again that is going to be the same throughout this entire discussion. The polarization vector, this is our initial polarizer sheet, and then we have our sample, okay, and the sample is loaded, and so as a result every point in the sample has two different directions, a fast direction and a slow direction. So in one direction the refractive index is larger, in the other direction it is lesser. We will call them fast and slow, that is customarily that is the terminology that people use, and there is an analyzer which has a polarization in this direction, okay. And just to be sure, if you are looking at let us say this point for instance, that point makes an angle theta with the x axis or with the analyzer direction, okay. So it's theta is going to vary from point to point depending on the orientation of n1 and n2 and depending on the orientation of the principal stresses, okay. So far I hope this is clear. So P and A are the linear polarizer sheets, and n, which we said was delta by 2 pi. Remember this, we call this a fringe order. This is a function of lambda and sigma 1 minus sigma 2 of course, and we also mentioned that if the initial polarization is unaltered, then it is cut off by the analyzer because it is perpendicular to the initial direction, and so this is the full sequence that we are going to follow. Now the question we have to ask is, when do you see a fringe? You see a fringe when delta by 2 pi is an integer, okay. Why do you need an integer? Well, if you had an integer, that means whatever light is coming in is not really being altered, or its phase is not being changed because it is integral multiple of 2 pi, and so it is going to get cut out by the analyzer, okay. If you had the analyzer in the same direction of the polarizer, then that light would come through, right. So that is why we are looking only at integer values. If the A was 90 degrees perpendicular to what it is right now, then we would be looking at half integers for instance. So the condition is, when does this occur? So that is the next question we have to ask, and really all the physics is really inside this question, right. It turns out there are two conditions or two situations under which this can occur. The first of course is obvious. So, you have sigma 1 minus, remember what delta by 2 pi was, delta by 2 pi, I will just write it here. So, this was, let us call this integer equal to m. So, this is delta by 2 pi lambda by h c. If you remember, delta by 2 pi was h c by lambda sigma 1 minus sigma 2, and so sigma 1 minus sigma 2 is this. So, this implies that sigma 1 minus sigma 2 is this integer m times lambda by h times c, c being a material constant, right. So, if this happens, then your total phase change will be an integer. So, the A will cut it out. So, you will get a black region, or not a black region, this particular region will get low intensity, right. Okay. Now, notice that this depends on lambda, right. So, this condition, this first condition under which delta by 2 pi is an integer, depends on the wavelength. So, if you have white light, so this is a white light source, then the constituent wavelengths, remember white light is made up of all the wavelengths, of course going from the blue end to the red end, maybe beyond. The different components will have this condition satisfied at different locations, right. So, you will not have, for example, if this is satisfied for red, then it is not satisfied for blue clearly, because m is not changing, h is not changing, c is certainly not changing. So, you have to have a different value of sigma 1 minus sigma 2, because lambda for blue is different from lambda for red. Okay. So, if it is satisfied for red, that means the analyzer will cut out the red light. So, the light you see at that particular point, so maybe I can write this down. So, if it is satisfied for let us say some lambda naught, then A cuts out this lambda naught. So, you will see all the other colors except red. So, light will shift towards the blue side, okay, if lambda naught is the red wavelength, and correspondingly if you have this satisfied for blue, then that will be shifted towards the red side, because that is cut out. Again, this is only because the A is perpendicular to the P, please keep that in mind. So, really if you have a body like this, so if I look at the z direction, if I look along the z axis and I look at this body and it is being loaded like this, let us say with some arbitrary tractions on its boundary, arbitrary forces on its boundary, it is going to really have a stress distribution everywhere here, okay, stress is going to be varying spatially. So, what that means is in some region the red is cut out, in some region the blue is cut out. So, you will see this nice rainbow type of pattern that comes up, and that is really what these fringes, if you remember our demo session right at the start, we showed you some of these images, and that is really because this condition is satisfied and this condition is a function of the wavelength, okay. Good. The second condition under which you will have this condition satisfied is a little bit less intuitive. This first one is of course quite intuitive, we just put down a value. The second one is less intuitive, and it happens when the p axis coincides with one of the principal stress directions. Okay, so let us say for example the principal stress direction, for example now P is vertical, it is along the y axis as we have drawn here. So, let us say at some point here, and let me use a orange, some point here the principal stresses are like this, right, along the x and y direction. Now, what happens is that the incoming light has only a polarization component along this y direction, right. So, there is no polarization along the other x direction or the other principal direction. So, the only component that is there is just going at one speed, and the other speed is not really coming into the picture because the other component is not there, okay. So, whatever is coming in is going through unaltered literally, and the analyzer being perpendicular to the polarizer will cut it out, okay. So, in this case irrespective of wavelength, the light intensity goes to 0. So, you will see black bands. If you use white light does not matter, if you use colored light does not matter, you will still see black bands. Okay. But in the first case you will see colored fringes, the second case you will see black bands. Okay. There are names for this. The first one is called an isochromatic. Again the name is indicative, chromatic comes from the fact that it depends on the color or the wavelength, and the second is called an isoclinic. Okay, clinic comes, well, not from a doctor's clinic, it comes from inclination. So, this is basically constant theta direction. So, remember in the figure I plotted or I have denoted this direction theta, which denotes the orientation of one of the principal axis with respect to the analyzer axis. It does not matter, pi by 2 minus that will be with respect to the polarizer axis, but at least one of those directions coincides with this, and so you get isoclinics here. Isochromatics are where sigma 1 minus sigma 2 is constant, right, and that is given by this right hand side delta by 2 pi lambda by hc, right. So, if you follow for example, if it is satisfied at one point for lambda naught and you have, let us say, that is a red value. So, it is 700 nanometers, let us say, then you get one particular peculiar color that is devoid of 700 nanometers. So, it looks bluish. If you take the same bluish intensity everywhere along this body inside, those will be the loci of sigma 1 minus sigma 2 being the same, right. So, that is how you use this information. Okay, good. So, now we know what to see. I mean, we have seen this before and now we know how to understand what we have seen before in the lab session. So, we need a way to formulate this problem. Okay. So, it is all nice and good to talk about it from this point of view, but then at the end of the day your aim is to get sigma x, sigma y, sigma x y at every single point. That is what you want to do, that is what photoelasticity does, and you can do that if you know the principal stress difference and the orientation of the principal axis, right, and that is what we are going to get. You clearly see that one set of information comes from one, the other set comes from the other, and so the aim is now to determine these values exactly and then how you can use that to reconstruct the stress tensor, right. So, for this we need a little bit of manipulation, mathematical manipulation. There is a term people call this Jones calculus, it is a little bit archaic the term, but it is very simple trigonometry, and just lets you keep track of what component is going where and what is being attenuated, what is the phase difference and so on, and it looks like the following. So, let us go back here and draw this fellow again. This is our z axis propagation direction, this is our light source, and this is our P, this is our object loaded, and this is our A analyzer. Okay. We are going to represent this equivalently as a set of 4 axes. So, this is the light source, okay. This symbol means equivalent, right. So, this is equivalent to an axis E1 which is like this, and in the material an axis E2 like this, a perpendicular axis E3 like this. So, E2 and E3 are perpendicular to each other, and let us say E3 makes, so E2 and E3 are on the xy plane. I hope my drawing is reasonably clear, so that because it is a 3-dimensional drawing, I hope it is not confusing, and this E3, this vector, right, these are 2 vectors, makes theta with the x axis. Okay, remember this is the x, and this is the y, and so on. So, this will also be theta. Okay. And then we have another one which we will call E4 and E5, and again these are parallel to E2 and E3, but they are a little distant away. So, same theta again. So, this distance between these two pairs of axes is h, okay, and that is the same as the thickness of the object h. And then we have an E6, and this is along the x axis. So, E1 is like our polarizer, E6 is like our analyzer, right, and that is along the x axis. And then it finally comes to you and you take a look at it. Okay, now let us break this problem down systematically. So, the first thing we need to do is look at the incident. Remember the 5 steps we spoke about. This is step number 1, step number 2, 3, 4 and 5. Okay. So, the incident wave has only E1. So, it only has a component along E1, I will call that E0 cos omega t, okay, because it is plane polarized. Stuff coming from the light source of course polarized in all directions, but then we are looking at stuff that is coming after the polarizer sheet. So, this is along the y hat direction. Okay. Now, the moment it enters the body, remember E2, E3 and E4, E5 are the entry and the exit of our body that is being loaded respectively. The moment it enters the body, it has to be resolved into 2 directions, E2 and E3. E2 and E3 correspond to the principal stress directions. Let us say well, at the risk of confusing the notation, I am just going to say sigma 1 and sigma 2, okay, E2, E3 is fine, do not worry about the numbers. So, the component of E1 along E2 is E0 cos omega t cos theta, and along E3 is E0 cos omega t sin theta. Okay. So, you are only taking this incoming vector, this vector, and you are resolving along E2 and along E3. Okay, so, you can write it as this times E2 bar and this times E3 bar. Okay. Now, the vector directions do not change, remember this is plane stress. So, the directions of the principal stresses are the same as you go through the thickness. They change from point to point, but they are the same as you go through the thickness, which means E4 and E5 are parallel, we have already drawn that, but because of the distance h and because they are travelling at different speeds, there will be a phase lag. Okay. So, the component along E4 will be the same as the component along E2, but now it will be omega t, let us say minus delta by 2 cos theta, there is a phase lag for one of them, and the E phi which is along the phi direction will be the same as E3, but with an additional phase advance, right. So, one of them will have a phase lag, other one will have phase advance. The relative phase between the two of course like we saw before is delta. So, I am going to just conveniently spread into delta by 2 and plus minus delta by 2 and plus delta by 2. Okay. If you take let us say E2 or E4 as the faster axis, so it is going faster, then you will have a plus here. If you take that as a slower axis, then you will have a minus here. So, the sign does not matter for now. Okay. Now, in E6 the component along E6 which is along the x hat direction is basically taking the E4 and resolving along E6 and adding E5 resolved along E6, right. So, it is E4 sin theta with a negative sign plus E phi cos theta with a positive sign. This is along E6 which is basically x hat direction, right. because the other component that is perpendicular to E6 is being absorbed by the polarizer shear. This guy is getting cut out, right. So, we only need the component that is in the direction of E6, direction of x hat. So, if you do this, you can write the E6 component as E0 cos of omega t plus delta by 2 sin theta cos theta minus E0 cos of omega t minus delta by 2 again sin theta cos theta, and I can open this up. So, let me rewrite that. Sin theta cos theta times cos of omega t plus delta by 2 minus cos of omega t minus delta by 2. The sign does not matter, plus minus can be exchanged, it does not matter, okay, depending on which is faster, which is slower. So, you can use cos A plus B cos A minus B and open this up, you will get E6 is equal to minus E0 sin theta cos theta sin omega t sin delta by 2 with a factor of 2. So, I will combine the factor of 2 with this and we will write this as minus E0 sin 2 theta sin omega t sin delta by 2, that is E6. Okay. Now, after E6 step 5 of course is to observe E6, right. Now, remember this light, the frequency at which the light is oscillating is omega, the electric field light, by light oscillating I mean the electric field oscillating is omega, and when you observe E6 you are typically going to look at it at a different sampling frequency of let us say omega naught. So, if you used let us say a standard movie camera, this omega naught is going to record 30 frames per second. So, that is 30 hertz. If you use a high speed camera, ultra high speed camera, omega is going to record at maybe 1 lakh frames per second or whatever 10 power 6 hertz maybe, the ultimate color high speed camera you can afford, and that is typically the frequency that you are going to be looking at. So, the time scale that you are going to be looking at is the inverse of this. So, it is like 10 power minus 6 seconds or a microsecond, and this of course is much larger, right. So, 30 inverse seconds whatever. Now, if you look at omega, for typical light the velocity of light is 3 into 10 power 8 meters per second. If you take the lower frequencies, which is the larger wavelengths, which is let us say red light for example, you have, even if you take a very high wavelength, let us say you go even to the ultra the infrared regime, you are looking at maybe 1000 nanometers, right. So, what is the frequency you are looking at here, C by lambda, which is 3 into 10 power 8 by 10 power 3 into 10 power minus 9. So, you are looking at 10 power 5. So, you are looking at 3 into 10 power 14 radians per second, you multiply divide by 2 pi, it does not matter. You are looking at something of the order of 10 power 14 or 10 power 15 hertz. Okay. So, if you want to be able to resolve this electric field vector doing its stuff and oscillating, you have to basically use a camera that has a shutter speed of 10 power minus 14 to 10 power minus 15 seconds. I frankly do not know of any camera that can do that. I do not think there exists a camera that can do that. So, typically your observation times are much larger than the time scale on which the frequency is going to be felt, right, or the time scale on which the electric field vector oscillates. So, that means the intensity that you observe, if you have studied electromagnetism you have probably seen this before, the intensity is proportional to the magnitude square of the magnitude of the field, right, proportional to E square. So the intensity goes like E0 square. I will leave out all the constants. So all the constants do not matter. So I will leave out E0. It will go like sine square 2 theta sine square omega t sine square delta by 2. And because the time scale of observation is much larger than the time scale of this oscillation, what you are going to actually observe is some averaged I, right, averaged over a time period of oscillation of the signal. So if you do that, again let me rewrite this on another page. So you have I goes like sine square omega t sine square 2 theta and sine square delta by 2. What you are actually observing is an average, time average. So the only thing that you have to time average here is the sine square omega t. So the time average of this is 1 by t tt, t being a time period or several time periods, it does not matter, it will cancel. This will give you some constant value pi or whatever, does not matter, it is a constant, right. So we take out all constants in the spirit of doing in the spirit of figuring out dependencies. So that goes out of the question. So the average intensity really depends on two factors, which is sine square 2 theta and sine square delta by 2. Okay. So when will you see 0 intensity? This will happen when either this term is 0 or this term is equal to 0, right. And when does that happen? This comes back to our two separate cases we discussed. So either sine 2 theta equal to 0 or sine delta by 2 is equal to 0. So this will happen when delta is 2 m pi, or delta by 2 is delta is 2 m pi, right. Sine pi is also 0, and this will happen when theta 2 theta is m pi, or theta is m pi by 2. M is an integer, right. So this is exactly what we discussed before. Delta of course is the same one that depends on the lambda and sigma 1 minus sigma 2, and this gives the condition for an isochromatic, and this gives the condition for the isoclinics. Okay. So remember, this sine 2 theta being 0 depends only on the orientation of the principal axis, which in this case we denoted by E4 E5 or E2 E3, that was the orientation theta that we had here. So the first condition depends only on the orientation of the axis, and the second condition depends on the h, it depends on the lambda and so on. So the first condition is valid for all lambda, right, and it is valid for all h, and it gives you the orientation of the principal axis. Okay. Now remember, because this is pi m pi by 2, that also comes out, right. So even if you rotate by pi by 2, the polarizer will then orient with the other principal direction, and then you will also get an isoclinic, right. So it is consistent even with that, and this fellow, like we discussed before, is dependent on lambda. So you will see colored fringes. Okay. So that basically tells us how you can interpret the regions of constant theta, regions of constant delta or delta equal to 2 m pi, and now you have contours of constant principal stress difference, contours of constant principal stress orientation, and from this the hope is that we should be able to reconstruct the stress field. Okay, that is basically what we do. Now there is one small problem, which is if you take monochromatic light. So if you take light of a fixed wavelength, exactly one wavelength, then the isochromatics will also look black, okay, and the isoclinics will also look black. So now you have a problem, you will see black fringes everywhere, I do not know which one is an isoclinic, which is an isochromatic. So there are a few things you have to do to figure out which are the corresponding contours, and then based on that you can actually get a map of orientation of theta and sigma 1 minus sigma 2, and from there we reconstruct the stress field, okay. So in the next session we will continue from here, and then I will work out the details of how this reconstruction can be done and how you can obtain the full stress field from point to point.